We've already talked about kinetic energy, as you know. What we've been referring to up until this point is actually a specific kind of kinetic energy, linear kinetic energy or translational kinetic energy. As you might guess, since we've been talking about rotational kinematics, we're going to look at rotational kinetic energy now. We know that our linear kinetic energy is 1/2 mv squared. From now on, when we're doing this, we're going to put a little t down here for translational kinetic energy when we're talking about translational kinetic energy. But if we think about the kinetic energy of a point mass moving around in a circle, okay, we can say that its kinetic energy is 1/2 mv squared. However, since it is moving in a circle, we can also say that v is omega r. Remember, this is not w, it is the Greek letter omega. It stands for rotational speed or velocity. So we can also say that this kinetic energy is 1/2 m r squared omega squared. So you can see that the rotation, this is how we frame rotational kinetic energy. It's related to the mass. It's also related to r, the distance the object is from what's called the axis of rotation, and the angular speed. Now, this mr squared is a particularly important quantity when we're talking about rotational stuff. This mr squared, remember this is specifically for a point mass, it's mr squared, but this is called the moment of inertia. And the letter I is used to represent moment of inertia. And this is kind of like the rotational equivalent of mass. Just like we have our velocity and our angular velocity. We have our displacement, we have our angular displacement. I, or moment of inertia, is the rotational equivalent of mass. And even just from this mr squared, you can see that this moment of inertia, it has to do with mass and where the mass is located relative to the axis of rotation. And even just from looking at this formula, you can see, obviously if mass goes up, then moment of inertia goes up. If mass goes down, moment of inertia goes down. From the r squared we've got there, you can see that as mass is located further from the axis of rotation, it increases the moment of inertia. As mass is located closer to the axis of rotation, that will decrease the moment of inertia. And that has a lot of consequences that we're going to talk more specifically about as we talk about different rotational quantities. For now, it's just important to know that if something has more mass further out from the axis of rotation, it will have a greater moment of inertia. So for example, if you have a hollow cylinder versus a solid cylinder, they have the same radius, and if they have the same mass, then the hollow one will have a greater moment of inertia because that mass is all around the outside of a cylinder and is therefore further from the axis of rotation. Granted, if it's hollow, it'll also likely have less mass, but if they have the same mass, then the hollow one will have a greater moment of inertia. Another important thing about moment of inertia is that the total moment of inertia is just equal to the sum of the moments of inertia of any objects that are part of the system or all the particles in an object. That means for a point mass, our moment of inertia is a simple mr squared. But for a three-dimensional object, it's a little bit more complicated to determine what the moment of inertia is. On page, what page is it? Page 314 has a little table down at the bottom of it that shows moments of inertia for different kinds of objects. For you calculus folks, to find a moment of inertia, you're actually integrating up, you're taking an integral of the mass over the volume of the object. But that's you guys aren't doing calc-based physics, so we won't talk more specifically about that. But just be aware that there are different moments of inertia for different kinds of objects. What's on this, the formulas on this page for different kinds of objects are not on your formula sheet because they're not given to you on the AP Physics test. So, in order for you to do well on your on the test when we have it, you will need to memorize those. And you'll need to know them for the AP test as well. So, make sure you do that. Right. So taking what we said that this is called R, we can then reformulate our rotational kinetic energy, and we can say it's just 1/2 I omega squared. Right. Since the mr squared is I, we've just got an I and an omega squared. Something I notice people tend to do is when they plug into this formula, they wind up forgetting to square omega. I think it's because almost always, this I has an r squared hidden inside of it. And so they square the r and they're like, okay, I just had to square one thing, so I'm done. But yeah, make sure you don't forget to square that angular velocity as well. So now we can see that our kinetic energy is made up of two parts. We have our translational kinetic energy, which we've already talked about, and our rotational kinetic energy, which is now new. Right. So if I asked you, for example, to find the total kinetic energy of the Earth as it revolves around the Sun, that would require two parts, because we now know that our total kinetic energy is equal to our translational kinetic energy plus our rotational kinetic energy. Right? And we know our translational is 1/2 mv squared. This is the mass of the Earth. And this is 1/2 I omega squared. And these are all going to be of the Earth. So there are two parts to the kinetic energy of the Earth. There's the energy, the translational kinetic energy it has as it rotates or revolves around the Sun, and there's the rotational kinetic energy it has as it spins on its axis. So we can look up some of these quantities. The mass of the Earth, as it turns out, is 5.98 times 10 to the 24th kilograms. The velocity of the Earth is a little bit trickier. We can figure this out because the Earth's orbital radius is 1.50 times 10 to the 11th meters. And we know that it orbits once around the Earth every 365 days. So we can do some math with that. So its velocity would be distance over time. Its distance, of course, is 2 pi r. That's the circumference of a circle. And we know our time is 365 days. And then we would need to convert 1 day to 24 hours, and 1 hour is 3,600 minutes. So then our velocity of the Earth is the very, very simple. See what I did there? That's a joke. It's not simple. 2 pi r over 365 times 24 times 3,600. I guess that isn't too bad. Squared. Plus 1/2. Well, moment of inertia of the Earth. We can say the Earth is pretty much a sphere. And looking at our handy-dandy chart on page 314, we can see that the moment of inertia of a solid sphere is 2/5 mr squared. So in here we can plug in 2/5 times the mass of the Earth, 5.98 times 10 to the 24th, times R then is the radius of the Earth, which is 6.38 times 10 to the 6th meters. 257 r squared times omega of Earth squared. And our omega is just our angle divided by time. So it's the same as the velocity, it's just 2 pi, it's just the same as the velocity without the radius, 2 pi over 365 times 24 times 3600 squared. So it may not be a simple number to punch into your calculator, but it takes up quite a bit of space on the board there, as you can see. But conceptually, there's nothing too tricky going on here. And you can punch all those numbers in and get a value, but I trust, as always, that you guys are capable of doing that. All right, so here we have a pulley, which I called a wheel. I don't know why I called it a wheel. It's a radius of 3 centimeters, and for the moment, we're going to say that the pulley is massless. And we've got a block attached to a rope that is wound around the pulley. Its mass is 1.1 kilograms. The bottom of the block is 98 centimeters off the ground. Now what's going to happen is we're holding this here, we're going to let go, and as we let go, then the wheel will uncoil and more rope will be let out, and the block will move its way to the floor. As this happens, this wheel is going to get spun along for the ride. So my question is, what is the wheel's angular speed when the block hits the ground? Now, in keeping with our massless pulley here, we're going to assume this is an ideal situation, that there is no air resistance, there's no friction. And therefore, our total mechanical energy is conserved. Which means that our KE naught plus PE naught equals KE final plus PE final. Now we're talking about when this block hits the floor, which means our final potential energy is going to be 0. And we're also saying we're releasing it from rest, so our KE naught is going to be 0. So in this case, we can just say that our initial potential energy is just the mass of the block times G times our height, which I have poorly selected to also be 9.8. And then our final kinetic energy is 1/2 the mass of the block times the velocity of the block squared. Because this pulley is uncoiling as the rope is let out, the velocity of the block, say this is the velocity of the block, is related to the angular velocity of the pulley by the same relationship that we've been working with, see, just equal to omega r. So, plugging that in, we've got omega block squared and radius of the block squared. And from that we can calculate the angular speed of the pulley. Right? Now, what if I change the situation?